Okay, so here's a list of derivative rules that we have. Today we're not going to do much trig, so that's why I don't have trig here. But if you forget some things, you can come back here. All right, so any questions on these formulas? So we've proved all these formulas. Okay, so today we're going to focus on something called implicit differentiation. But first, let's think about what an implicit function is. So first, let's think of a good definition. A curve is differentiable if there exist tangent lines at every point. So I should amend this a little bit. Differentiable in a region. If there exist tangent lines at every point. So for example, the circle is actually a differentiable curve, except for a couple points. Circle is differentiable except for 2 points. Can someone say what the 2 points are? Like if I draw it, where do you think the 2 points would be that it's not differentiable? In other words, where is a tangent line kind of weird? You can use the cardinal directions. So first of all, why is it differentiable? Because it makes sense to talk about a tangent line for most places, right? Well, where is it weird to talk about a tangent line? What's the awkward point here? Where y equals 0. Yes, good, where y equals 0. So maybe I'll do it in red. Yeah, where y equals 0, what happens at y equals 0? Why is this tangent line weird? It meaning the slope. The slope is undefined. So something is weird about those 2 points, but if you agree that everywhere else is fine. So we're going to describe why everywhere else is fine. Okay, so this is what the implicit function is. So this is really used for curves that cannot be described explicitly as a function. Curves that cannot be described explicitly as a function. So for example, the circle, right? A circle cannot be described explicitly as a function. Why not? Why is it not a function? Not the horizontal line test. That's one-to-one test. It's the other one. Yeah, vertical. Where you have two y's. You have two y values for the same x value. However, again, there can be a way to describe the circle, which we know ways to describe, is that if we take so this is the implicit function. For x0, y0 on the curve, there exists a region around the point such that it can be expressed as a function, such that the graph in the region can be expressed as a function. Okay, so what does this mean? Y equals f of x. So what does this mean in the circle? Take this point here. Even though this whole thing is not a function, let's take this point here, x0, y0, and let's look at a region around that point. Let's just take this little region. What does the graph look like in this region? It looks like the arc of a circle. That makes sense? So right now what I'm really doing is erasing the rest of the circle and just looking at that little section there. Everyone see what I'm doing? Yeah. So, is this a function? This little bit is a function. Why is that a function? It passes the vertical line test, right? Why wouldn't it be just a point? It's in particular a region, so there has to be a little area to this. I'm purposely being not technical because there's a lot more to this, but well, actually, the idea, if you think about it, the idea is that I'm kind of like, if you think about it, I'm like kind of like patchworking the circle. So for every point, I can do this. So I'm like taking these patches and making the circle. That's kind of the idea. Except for these points. I can't do it for these points. Yeah, there's a so this, if I just look at this specifically, that is a function, and ignore everything else, that's a function. So if we think about these problem areas, we can see that there is not an explicit function that describes these areas. So there's no region I can make where the function is one-to-one. So let's look at this. No matter like how I draw this circle, it's always going to look like this around the the east and west poles. That makes sense? No matter how you look at it, it's always not going to be a function. It's never a function. So before we even talk about the derivative, right, we can see that this will not be differentiable here. Well, cannot be described as an implicit function. Like no matter how small of a circle we make, right? There's always still going to be a bit of stuff that's going to be contained in a vertical line. Okay, so we know what this function is for a circle, these implicit functions. But first, any questions just on the idea there? Essentially, we're saying that what we can do to get around the fact that this is not a function, we can say, well, let's not think about the whole thing, but let's only look at specific places that we really care about. Then we can actually describe this. And then what we're going to do is actually talk about the derivative. So once we describe this implicit function, and implicitly, like we can patchwork the curve and describe it. Then we can describe, how do you define the derivative? Well, the idea is the derivative is going to be on this curve, right? So it's going to be like of a different curve at every point. So for example, the circle, x squared plus y squared is equal to 1. Lagging a bit. It's probably my computer is just being slow. But yeah, if I cut off and you don't hear what I'm saying, you know, I can repeat it, so let me know. Okay, so we know this is the equation of a circle. And what if we solve for y? What happens? We get y squared is equal to 1 minus x squared. And then what's our next step? How do we solve for y? Yeah, square root both sides. So now it's very important when I do the operation square root, I do consider plus minus. Right, but square root as a function is just plus, so just keep that in mind. So this is why the circle is not a function. But what's the implicit function? We can say the circle is two things. It's positive 1 minus x squared when what? And it's negative 1 minus x squared when what? When y is greater than 0, we look at this function, square root of 1 minus x squared. When y is less than 0, we look at this function. So that's why we have the two semicircles. So this one is 1 minus x squared. And this one is negative 1 minus x squared. So these are the implicit functions. So what's the implicit function of a circle? Well, you take a point and you say, if the y value is positive, then the implicit function is 1 minus x squared. However, if you take a point and the y value is negative, then the implicit function is negative 1 minus x squared. Why don't I include y equals 0 in my implicit function? Yeah, I cannot describe that area implicitly, right? I don't, there's a problem at these points. Cannot be described implicitly. Okay. All right, so any questions on that? Okay, so what is the idea? Now we're going to take a derivative. Okay, so y is an implicit function. Right, again, when y is less than 0, y is equal to 1 minus x squared. Sorry, this should be greater than 0. When y is less than 0, y is equal to negative 1 minus x squared. Both of these are differentiable. Do you agree? We can chain rule that. Okay, so what is the derivative, dy dx? Well, all of these things are differentiable. Right, what's the derivative of x squared? 2x. Now, what's the derivative of y squared? Y is a function of x. Almost, yeah, it's 2y, but we do chain rule. This is why we did here, right? What is the derivative of gx squared? It's 2 times g prime. So what is the derivative of y squared? Well, since y is a function of x, 2y, I like this notation, dy dx, or y prime is fine. I sometimes see students kind of mistake the y prime. But we don't know what dy dx is, right? We don't know what, this is what we want, right? We don't know what this is yet, but we know it exists implicitly. Yeah, so let's just make this clear. D dx of y squared, chain rule, 2y dy dx. So this is x squared composed with y. Okay, so any questions why the derivative of y squared is 2y dy dx? And again, it's not the derivative of y squared. So yeah, so this is a very important thing. The derivative with respect to x. So if you want to think about that is like you're observing how y squared is changing with respect to how x is changing. So this is a lot different. If you want to think of like independent or dependent variable, right? The dx is kind of like your seconds, and the y squared would be like your distance. Yeah, so just make sure understand the difference. Okay, anyway, so what's the derivative of 1? Zero. Okay, so now we have that 2x plus 2y dy dx is equal to 0. And what we want to find is solve for dy dx. Right, that's what I want to find. See what I'm doing here is like I have this equation x squared plus y squared equals 1. And if I take the derivative of everything, it gives me an inequality. Taking the derivative of a true equation gives a true equation. Similarly to like, think of this as similar to like multiplying by 2 on both sides, subtracting 1 on both sides. You know, the derivative is doing the same thing. I'm taking the derivative of both sides. Okay, how do we solve for dy dx? Yep, subtract 2x, and then what? Yeah, put that over 2y. So it's negative x over y. Okay, so let's do new page. So we have x squared plus y squared is equal to 1. And then we just found that dy dx is equal to negative x over y. All right, so what we can do here, if we want to make it even nicer, sometimes we don't have to do this, but notice that y is equal to square root of 1 minus x squared and negative 1 minus x squared. Right? So what we could say is this is equal to negative x over square root of 1 minus x squared, and it's equal to positive x over square root of 1 minus x squared. Where is this true? For what y values is this true? Let's do the first one here. Yeah, this one's bigger than 0 because I replaced this one. And this is less than 0. Okay, so let's think of a practice point, point. Okay, someone give me their favorite point on the unit circle. That's not 1, 0, and 0, 1, and negative 1, 0. What's another point on the unit circle that you know? Okay, yeah, so it would be cosine pi over 4 and sine pi over 4, right? Cosine pi over 4 and sine pi over 4 are points in the unit circle. Yeah, so these points are radical 2 over 2 and radical 2 over 2. Okay, so let's draw it. So if here is that point, here's the tangent line at that point, and let's plug it in. In some circumstances, it's nicer to write this. But if you can see, if I know the 2 points, it might be easier to use this equation. What is the slope of the tangent line? At this point? Yeah, -1. So square root 2 over 2 is the x, and square root 2 over 2 is the y. So that makes -1. This is using this one. Do you see that? So this is the derivative at that point. So this is, again, it's hard to say that. Implicitly, this is the slope of the tangent line at that point. Okay, so we can actually find the whole tangent line, right? Y minus y0 is equal to mx minus x0. What's x0 and y0? Well, it's exactly the point, right? Right, which is radical 2 over 2 and negative radical 2 over 2. Okay, so just solving, get negative x, and it's going to be plus radical 2. Okay, cool. So questions about that? Okay, so let's do another circle. Okay, anyone remember the equation of a general circle? So if x squared plus y squared is equal to 1 is the unit circle, how do you generalize that to any point and any center? Any center, any radius. Yeah, good. So, yeah, so I like h and k. That's fine. I'll use h and k. Yeah, we had it as general radius, but this will also be general center. Okay, so h, k, and r are just numbers, by the way. Okay, let's find the derivative, implicitly. Okay, what's the derivative of the first thing? Right, this is a chain rule, right? I have x minus h as one function, and I have x squared as another function. So I have 2 times x minus h, and then times 1. Good. Okay, what's the derivative of this one? Close to y minus k, but do I have to include anything else? Yeah, I need that dy dx. This so, right, because the derivative of the inside, the derivative of y minus k is dy dx. So this is also chain rule. Why don't we need a dx here? What's d dx of x? Yeah. So that's why we don't write that. So we're not giving y special treatment. We're also doing it for x. But notice the derivative is just 1. And what's the derivative of r squared? What's r? Yeah, r is a number, remember. R is not a function of x. It's just 0. Well, it is, but it's a boring function. So always be wary of that. R is a number. Okay, let's solve for dy dx. So by subtracting and dividing, we get this. What's something mysterious about this? What should puzzle you about this answer? Or not puzzle if you kind of see the picture. What's missing in the derivative that you might expect to be there? Or not expect if you understand the derivative? Like what's missing from the general equation of a circle to the derivative? What's not there? Y and k are there. Oh, when y is equal to k, sure. The problem, I mean, something just like even more surface level. Yeah, there's no r. No r in the derivative. And that is really weird. So circles of any radius have the same derivative. And it's kind of, I mean, this shouldn't surprise you, based on like what a circle is. The idea is that no matter what the radius is, how it's changing is always the same. Right? So these are various tangent lines at some point, and they're all the same. The slope is the same. They're all parallel. Right? So no matter where you plug in your values, they'll always be the same for the same x, y. All right, so I think it's interesting to note. Yeah, so questions about that? I think it kind of goes to show like kind of a nice thing about a circle. So the circle, it's really small. and a circle that's really big, they have the same expressions of their derivative. Okay, so one thing I want to talk about before we go on to other types of shapes is just something from geometry which you may or may not know. Conic sections. Anybody know some conic sections? Like, what are the conic sections? Yeah, hyperbola is an example. What are the other ones? Parabola is another one. Do you know any others? Ellipse, and one more. Yep, circle too. Okay, do you know where that comes from? Why is it called conic? Well, conic comes from cone. So, there's a mathematician, ancient Greek times, Apollonius, and he wrote a big treatise on conic sections. So, why are they called conic sections is that they're curves that are gotten out by cutting a cone. So let's do the circle first. How do you define a circle? A circle is defined by a perpendicular cut to the axis of a cone. So if you cut this cone at a perpendicular angle, the shape that pops out is a perfect circle. Okay, so this is a circle. Okay, what do you think an ellipse is? Yeah, it's a slice at an angle, but it can't be too harsh of an angle, right? Yeah, if you take it has to be angle at, yeah, we'll describe, so when we talk about the parabola, we'll describe how much of an angle that is allowed to be. Right, so if you take that cut, so actually, if you really want to see it vividly, if you like take the bottom half, this is the circle. And then if you were to take the bottom part here, this is the thing that pop out, and this is an ellipse. So this is at a right angle, and not at a right angle. Okay, how else can you cut the cone, you think? With respect to the axis. And maybe these lines can come into play too. Yeah, good. The hyperbola is a cut that is parallel to the axis. So the shape that pops out like this. So if you were to bring that outward, it would be something like this. So these things would be the hyperbolas. And what's one last way you can cut a cone? So you can do this like to any to like a traffic cone. Right? It doesn't have to be this double cone. Hyperbola doesn't have to be like both of the upper and lower. So hint is it relies on this on these lines. So if you take a cut that is parallel to one of these, that's what makes the parabola. So picture looks something like that. So this is the parabola. Anyway, I thought it'd just be fun to kind of, if you haven't seen this, I think it's cool to see. But if you have, I think it's good to remind yourself of this. But so that's why they're called conic sections. So we can find the derivatives of all these conic sections. Let's start with the ellipse. Well, probably we already know. So the other ones are more interesting. Let's do the ellipse. This is a general equation for the ellipse. It's x minus h squared over a squared plus y minus k squared over b squared is equal to 1. So HK is the center of the ellipse. B is the height of the ellipse. And A is the height radial in terms of radius. So if you want to think really, so 2B would be like the height, and 2A would be the width. But A and B are these respective widths. So let's do a derivative. Okay. So A and B are just numbers, and H and K are numbers. Can I express this differently to maybe make it easier for the derivative? What can I do to this equation to make it a little bit easier for the derivative? Yeah, actually, instead of common denominator, I can't get rid of squares, right? Square rooting couldn't do that because of this plus, right? I can't square root over plus. It'll just kind of make it more complicated. So just be wary of that. So instead of common denominator, I would just say multiply by the common denominator. So if I multiply by AB squared, I get this. And I think this is this might be easier. Well, yeah, you can say it's common denominator then multiply by AP squared. But okay, so let's do the derivative. And then after we do the derivative, we can take a short break. Okay, how do you take the derivative of this first thing? Do I need product rule for this, or do I not need product rule for this? Why do I need product rule? To be, well, I need an x in here, right? For the derivative. Okay, you don't need a product rule. Someone say maybe why you don't need a product rule? Oh, I see what you have, e is it's close, but not 2b, but 2b squared, yeah. Yeah, so you don't need product rule because remember b is just a number. Right, so it's by the constant rule. So you can just leave that alone and then just look at the rest. So we've done that one before. It's 2x minus h times the derivative of x, which is 1. Or 2b squared x minus h. Okay, and then the next one, similar idea. A is a constant, so I can just leave that out. And 2y minus k. And do I have to remember something? Yes, I need that dy dx. That's the derivative of y by the chain rule. And then what's the derivative of a squared b squared? Zero, because remember, these are just numbers. Okay, so solving. What do we get? So from here, it's just solve for it. Negative 2b squared x minus h and 2a squared y minus k. So it's negative b squared x minus h over a squared y minus k. Okay, cool. So that's the derivative. What happens if what happens if a is equal to b? Yeah, then it's a circle. So the general ellipse is actually a general circle. A circle is a type of ellipse where a and b are the same. So it's just one note. So notice in the ellipse, they don't disappear. These two terms here. If a was equal to b, then these would disappear, and we get what we had before for the circle. Right? Remember, in these case, they were 1. Or they already canceled it out because we didn't have any terms there. Okay, yeah, so we'll take a 10-minute break. Maybe meet back at 6:42. Yeah, so stick around for any questions if you have. I'll back around, 6:42. Okay, so let's keep going and do the hyperbola. So that's the other one that we haven't done yet. Okay, so So hyperbola, the unit hyperbola is x squared minus y squared is equal to 1. Okay. By the way, speaking of hyperbola, this looks familiar, right? This looks very similar to what curve that we know? It looks like almost x squared plus y squared is equal to 1, right? So if you remember cosine and sine, were generated from this equation, right? Cosine squared plus y squared is equal to 1. So there are similar equations for hyperbolas. So if you're interested in hyperbolas, there's a whole part of trigonometry that is based on this equation. They're called hyperbolic trig functions. So you can define new functions that's called hyperbolic cosine and hyperbolic sine, such that these mysterious functions, that when they are squared and subtracted, they equal 1. They're just interesting. So I don't know, maybe a little fun math exercise. Try to make your own trig system based on this equation. Based on this, you can construct a lot of different identities. You can find derivatives based on this, if you think about it a little bit. But it's something that you might do on Calc 2. You might talk about it. But anyway, that's just an aside. Let's take the derivative of this hyperbola. Okay, so what is it? What's the first line here? Derivative of x squared. Two x. Derivative of y squared. Did you forget something, or dy dx? Good. And what is it equal to? 0. Okay, solving. We get dy dx. This time is equal to as x over y. Okay, so let's think about this. All right, so this is written this way. This is what the hyperbola looks like. Okay, so let's think about why this might make sense. When is this positive and when is this negative? When is dy dx positive and when is it negative? In terms of quadrants? How about over here? Is x over y positive or negative here? It's positive. Is x over y positive or negative here? Negative. Is x over y positive or negative here? Positive. Right, they're both negative. And x over y is positive or negative here? Yes, negative. Okay, so this makes sense based on our picture, right? All tangent lines over here are all pointing upward. All tangent lines here are all pointing downward. All tangent lines here are all pointing upward. And tangent lines here are down. Right, so it's reasonable. All right, so this one was actually not a bad one because it's a simple form of the hyperbola. Okay, so I have some other ones. Let's do the lemniscate. So lemniscate is the infinity symbol. So here's the general form. This one's a bit more complicated. X squared plus y squared squared is equal to 2a squared x squared minus y squared. So what is A? A is here and here. See, there's two foci. And these are actually generated by the hyperbola. So there are hyperbolas here. Actually, maybe I can bring up the picture. Just give me a second. Wait, sorry, it's a little slow. Oh, where is it? Oh, here it is. Okay, so I just uploaded a picture of kind of how the lemniscate is being drawn. It's just a fun fact. All right, but let's take the derivative of this. Can you all see the picture, or is it a GIF? All right, cool. Yeah, it's just fun. Okay, let's take the derivative. Okay, so it's a bit more complicated here. How do you do the derivative of the left-hand side? Chain rule, yeah. So what is the first part of the chain? Like, what's the grand function that you plug into? Yeah, x squared. So first, so the derivative of x squared is 2x. So it's 2 times what's ever inside. And then I need the derivative of the inside. What's the derivative of the inside? Not the extra 2, but 2x plus 2y, and then dy dx. But okay, I guess the 2 outside from before. So, but do remember that you need to, like, this is the g of x, and this is like the g prime of x. Okay, yeah. Okay, so let's do the other side. This one's actually not as bad. What is it? Remember, a is a number. Yeah, 2a squared left outside. And the derivative of the rest is 2x, then minus 2y dy dx. Okay, so after we've written this first line, the rest is just algebra. So we're done with the calculus. So this is, funny thing about calculus is that the actual calculus it's going is not too bad, right? As long as you just memorize those formulas, right? But the hard part is just, can you do algebra? So let's simplify this up a bit. Here's a 2 and there's a 2. We can get that out of the way. And then we need to distribute, right? What are we trying to do? We're trying to solve for dy dx. Why would I need to distribute? What's the goal? How do you solve for a term? So I jumped the gun by saying to distribute. How do I solve for dy dx? How do you do that? Just what would your steps be? What would your main goal be? How do you solve for dy dx? There's multiple terms that you need to solve for. What should you do? Yeah. So yeah, that's true. And you find the coefficient for dy dx, but how would I begin to solve? Right? These are all. How do I solve for 2 dy dx's? Right? There's 2 of them. Maybe not understand what I'm asking. Saying just put all the dy dx's on one side, right? That's always when you solve for a variable. You put them on both sides. So I would need to distribute this out and put all the dy dx's on one side. So let's distribute it out. We have 2x cubed plus 2x squared y dy dx plus 2xy squared plus 2y cubed dy dx is equal to 2a squared x minus 2a squared y dy dx. Okay, now does my question make more sense? How do you solve for dy dx? How do you solve for dy dx here? Or it's just algebra. There's no calculus is done. So now we go back to last year. Yep, just move all the dy dx's on one side and the not dy dx's on the other. So here are the not dy dx's. And here are the dy dx's. Sorry if I'm sounding pedantic, but this is where a lot of people mess up, is on not knowing how to solve for dy dx. It may look complicated, but again, it's not much different than just normal algebra. Okay. Can I make this a fraction bit cleaner? Has everyone followed what we're doing? No, it's a lot. A lot of 2's there, right? In fact, they all have 2's. So let's get rid of that. Yeah, good. Divide by 2. Okay, so now how do you solve for dy dx? So what was the whole point of moving all the dy dx's to the left and moving all the others to the right? Yes, they can factor out dy dx. One recommendation, if algebra is intimidating and you don't like dy dx, replace it with any letter that you want, right? They're just symbols. They don't mean anything. I mean, they do mean things, but without context, they mean nothing. So they can be anything you want them to be, as long as you say what they are. If you like y prime better, I know sometimes it's taught as y prime. You can write y prime, or if you like f or h, you can write that too. I just like dy dx because, I don't know, I sometimes see people do this, which is not good. Yeah, dy dx and y prime are the same. But sometimes y prime, I think, can get confusing, especially if you're first time dealing with it. You might confuse the prime as an exponent. So it's up to you. But I personally like dy dx just because it's like complicated enough that I know like how it's different than the rest of the things. The y prime can get a little too many things going on, or too many similar things going on. Anyway, so this is the derivative. One thing to note is that, can someone say why the derivative at 0 doesn't exist? If you plug in 0, 0, it doesn't exist, right? What happens when you plug in 0, 0? What do you get? Yeah, you get 0 over 0. However, there's no like vertical line going on at 0, 0. Yeah, so what problem do you think is 0, 0? What's wrong with 0, 0? Yeah, and why would that be a problem? A couple of reasons can be your answer. What's wrong with intersecting yourself? Not cancels out, but yeah, you can think about the slope. Think about limits. There's actually 4 ways you can take a limit, right? There's a lot of ways you can actually approach 0. Yeah, there's multiple slopes. So remember, the derivative exists only if the limit exists. But there's actually 2 slopes that's happening that it approaches from some directions. Right? On the one hand, approaching the line, or the origin points to this slope. On the other hand, when you approach, it points to that slope. So that's a problem for derivatives. Another reason is that if you take a little region around that point, will you ever get a function? No. So 0, 0 is not, cannot be implicitly defined. Well, at least it cannot be implicitly defined this way. In Calc 2, you'll figure out another way you can define it. It's actually more intuitive, another way you can define it. Can anyone guess how another way you can define the curve? And it's actually based on what I sent. You can define a curve by just drawing it. So something you'll talk about in Calc 2 is called parametric equations. So like where your variable is time. So what I'm drawing is the function. So like this going in time is the function. So I'm drawing one thing for every second in time. So that's why it's a function. One output per input of time. But so you do find ways to get around this problem in Calc 2. But for here, these are Cartesian coordinates. It's called the derivative does not exist at 0. Okay, so any questions about the lemniscate here, the infinity symbol? Okay, let's do like a word problem. So this is a word problem I had in when I looked at the homework. So you might have different numbers, but it requires some critical thinking. So I thought I could just do what the template is. But I recommend when you look at this problem, don't, think about it before looking back at how we do it here. So I'm going to paraphrase. So you have this ellipse-shaped object, and you shine a light onto the object, and it casts a shadow. And the shadow ends at -5, 0. And the light stands at 3, 0. And the ellipse-shaped object can be defined by the ellipse equation, x squared plus 4y squared is less than or equal to 5. So why the less than or equal to 5 bit? It just means the inside. So the ellipse is actually stuff inside, and then the boundary of the ellipse is x squared plus 4y squared equals 5. Oh, by the way, I'm not sure if maybe anyone has told you, you know the circle is just the outside of the circle, right? When you say area of a circle, you're really saying the area of the inside of the circle, which is actually, this is called a disk versus a circle. Oh no. So the disk is actually x squared plus y squared is less than or equal to 1 versus x squared plus y squared is equal to 1. If you ever see that, you know, this is an example where you do see that for the ellipse, but just so, a little fun fact. Okay, so the question is, how tall is the lamp? Okay, so there's a lot going on here, right? Before I give it away, what do you think are pieces of information that we know that we can figure out? You know, what do you think are some things that we can figure out? Or what do you think could be helpful? Maybe a better question, what piece of information will give us the answer immediately? There's one thing, if I knew one thing, we would know the answer. Oh, distance of lamp and the end of the shadow. That could be helpful. We could put that in there. It may not be necessary, but that is something we do know. I'll give a hint, it's not a triangle. Yeah, actually the tangent line will give us the answer immediately. Why would the tangent line give the answer? If we know the tangent line, we know the answer. Right, right. So where is the lamp? Well, it's sitting at 3, and the height of it is 3 comma y. Right, so this would be the height. The light source is centered at 3 comma y. Okay, so tangent line, that's a necessary thing we need to know. What do we need for the tangent line? What pieces of information do we need for the tangent line? Yeah, we need the derivative of the ellipse. What else do we need? Is the derivative of the ellipse enough? In addition to the derivative, right? What do I need? What don't we know? Let's say if we found the derivative of the ellipse. Good, yeah. Just having the derivative of the ellipse isn't enough, right? Because how do we know what to plug in, right? We don't know what this point is. So we need to know the point on the ellipse. That the tangent line hits. And how do you find that out? Well, maybe the -5, 0 is a point on the line. Okay, so can you see why these, so really the combination of these two can establish for us the answer. So we need the derivative of the ellipse for the reason for the slope. But the problem is that we don't know what point to plug in. However, knowing that the point has to go, the line has to go through -5, 0, maybe we can figure out from that piece of information. Okay, so let's do that. So let's do new picture. So the point -5, 0. This is the lamp. And this is 3, 0. And we have x squared plus 4y squared is equal to 5. Okay, yeah, so let's find the derivative of the ellipse. Let's dy dx. Let's just go part by part. So what's the first part? Derivative of x squared, 2x, and then what's the derivative of the next 4y squared? Okay, 2y dy dx, and then multiplied by 4 is 8. No, you're right. 8y dy dx. And then what is that equal to? 0. Okay, so solving. We get -x over 4y. All right, so we need the equation of the tangent line. What two pieces do we need to know for the equation of a tangent line? What two things do we need? We need the slope, and we need a point. What's a point that we know? What's a point on the line that we know? -5, 0, good. What's the slope? Good, yeah. So it's unknown, but must be of the form -x over 4y. Okay, so we have y minus 0 is equal to -x over 4y, x plus 5. So xy is a point on the ellipse. Okay, so let's clean this up a bit and multiply by 4y. Okay, now what? This is true. And I need to find xy. That's the goal, right? How do I solve this? So what is true about xy? It needs to be a point on the ellipse. What equation tells you a point on the ellipse? What equation tells you the point on the ellipse? Right, so this is not the ellipse, right? This is just a point on the line. Yeah. So this statement here, these are all, so x squared plus 4y squared is equal to 5. If xy satisfies, then xy is on the ellipse. That's what that equation means. Okay, so how can we marry these two equations? So both these things need to be true. For xy to be on the line and xy on the ellipse. Right? A couple approaches at this step. So two things need to happen. Again, what am I solving for? I'm solving for this line, this point here. It's the line that's both on the tangent line and on the ellipse. Substitution would be easy. So just to reiterate, I'm solving this system. If you remember systems of equations, it's like that's what I'm doing. How do you solve systems of equations? Do you remember? There's two ways, substitution or elimination. Yeah. 4y squared is equal to negative x squared minus 5x. And here's another 4y squared. So this makes x squared plus negative x squared minus 5x is equal to 5. Everyone see what we're doing there? We have two equations. X squared plus 4y squared is equal to 5 is the ellipse. And you have the tangent line, 4y squared is equal to negative x squared minus 5x. What point satisfies both of these? It's precisely the point that we want, where the ellipse hits the tangent line. And so by substitution, we get negative 5x is equal to 5, x is equal to negative 1. Okay, now what's the y value? So I need just plug in x equals -1. So the ellipse is the easier place to plug it in. -1 squared plus 4y squared. Oh yeah, is it 1 or -1? It's actually one or the other. Yeah, why is it +1? Because I'm not on this side, right? I'm on this side. This is -1, 1, and this is -1, -1. It's actually only one of them. Or the other, if we did the other side, that would be in the wrong direction. Okay. Let's just do a new page, and then we have x, y is equal to -1, 1. This is the point on ellipse and line. We have dy dx is equal to -x over 4y. Okay, yeah. All right, so I'll just zoom the rest of it. So our equation of the line was y minus 0 is equal to m x plus 5. If we plug in -1, 1 to get the slope, we get 1/4. So y is equal to 1/4 x plus 5. And now what we cared about was when x was equal to 3, right? That was this. It was 3, and this was the point. So we plug in 3, and we get y is equal to 1/4 3 plus 5. Y is equal to 2. So that's the height of the lamp. Okay, that's it. So I'll stop the recording now.